I thought I'd do something a little different from usual in this video, and that is to build up a game based on the old Simon game from the 1970s. I was inspired to do this by, there's a teardown video that bigclive.com had, and I'll provide a link below. And he took apart a real Simon, and I thought it'd be an interesting exercise to kind of build up one using an STM32F411CE, also known as the Black Pill, which you can see right here. And in that exercise, I could demonstrate a few things. The first one's how to build some simple STM32F4 circuits that has some LEDs on output, buttons on input, PWM peripherals. I thought it'd be interesting to show how you handle these peripherals, specifically in C++, using the STMCubeIDE environment. And then finally, sort of some programming on how you manage game state within the typical response loop of the STM32 chipset. So all the code and the schematic for what I've built up here is up on my GitHub repo, and I'll provide a link below, and feel free to use that in any way you see fit. If you get enjoyment out of it, that's good enough for me. I do have to have a shout out for a link that I did found where a gentleman went through and did a complete reverse engineering of the Simon, in particular sort of derived all the tone frequencies and so on and so forth. Anyway, that's a great link, and it was very helpful in building this up. So for those of you who aren't old like me and haven't seen what Simon is, let me just show you how it works. And so basically it's you go through and it plays a series of tones and you have to copy them. So let me start the game up. So now I have to press yellow, yellow, green, yellow, green, green. And if I get it wrong, it tells me. Obviously if I get it right, so let me start the game up again. Let me get it right this time. And there you can see that was a successful run of the game. Okay, so let's pan up to the schematic up here, and let's see how it's all wired together. So basically I have, make sure you can see all that, I have 4 input switches here. These input switches are for the yellow, blue, red, and green tones, and each one of those switches is just a simple path to ground when the switch is pushed. I've also got the 4 yellow, blue, red, and green LEDs right here. They're connected up to 5 volts at the anode, and then they go through, each goes through a 220 ohm resistor, through a 2N3904 transistor, which is just configured as a switch here, and then that gets turned off or on based on a signal from the Black Pill through a 3.3K resistor. So if this is high, 3.3 volts is high here, this will turn the transistor on, which will turn the LED on. Now I could have probably driven the LEDs directly to the pins. These pins, I believe, can sync up to 20 or 30 milliamps, so I probably could, but I thought I'd put the transistors in there just for a simple bit of safety factor. So the next part of the circuit is the tones themselves, and they're generated through PWM, pulse width modulation. And I'll go through the code behind that, but effectively what you do is you get a square wave out of here, which is at the frequency of the tone that you want to do. So these tones are around about 200 to 400 hertz. So I get a 200 to 400 hertz square wave out of here. And then that gets fed in through this pot here, which just acts as a simple volume control, through to an LM386 amplifier, and then finally off to the speaker. So it's all pretty simple here. I don't need to amplify the signal very much. Basically, I do want to buffer it from the I do want to buffer the signal though from the STM32F411. And then finally down the bottom here we have the power supply. It's a simple 7805, 12 volts in, some filtering caps here, and then 5 volts out. And there's a convenient 5-volt pin on the STM32F4 here. Just panning down here, let me just walk through. So here's the regulator down the bottom here. I'm feeding in the 5 volts here. Obviously I've got a ground here. And then here's that volume pot and speaker. And then finally over here an LM386. So that's basically the setup. As you can see, it's a pretty simple circuit. A lot of the complexity is actually in processing the signals from the peripherals. So what I'll do is I'll move now onto the code itself, and we can have a look at that. Just a quick note before we get started in the programming. I'm connecting to the Black Pill with STLink V2. This is the genuine one. There are actually other ones that you can buy off eBay and other places. This is an example one. Let me hold it up the right way. Now, interestingly, this one actually doesn't work with the Black Pill. Not quite sure why. Could be to do with the fact that I need to hook up the reset line. I'm not entirely sure, but this guy doesn't work. This guy does work. I've had the situation where in other cases this guy hasn't worked and the other programmer has worked. But anyway, going to be using STLink V2 for this. So let's move on to setting up the project. So I've started up the STMCubeIDE, created a new project. So let me pick my board now. It's an STM32F411CE. So there it is there, and it happens to be the UFQ version of that. So let's go through, create it, and let's call it test 411. And it'll go through and basically create the project, and it'll get you straight into the STM32Cube configuration tool, which allows you to configure all the pins on the board. It does usually take a little while to get started, so I'm going to stop it here and then I'll come back when it's done its work. Right, so let's set up the PWM. So the PWM on the STM series is easily accomplished with through timers. Now, timers themselves is a very deep topic which I don't plan on covering, but the timers here are TIM1 through TIM11, you can see here. So I'll pick TIM4. And now to start to configure it, I want a trigger source of ITR0, enable the internal clock, and then I'm just going to be using one of these channels here. You can configure this so that it outputs multiple PWM signals, but let's just configure one, and I want PWM generation channel 1. And then the rest is accomplished using the parameters down the bottom here. So let's have a look at those in a little more detail. Okay, so the actual frequency of the timer itself is governed by at least 3 variables. There's a few more that we'll cover, but there is the prescaler, the counter period, and the clock speed of the CPU itself. Now, the clock speed of this CPU is 100 megahertz, and I've enabled that through the clock configuration. So you can see here, this is the clock configuration tool, and out of the box it comes set to 16 megahertz here. But here is this value here is the clock speed of the microcontroller itself, and you can see I've got it set here to 100 megahertz. The actual formula that you use to calculate frequency is basically the clock speed, which is 100 megahertz in my case, divided by 1 plus the prescaler times 1 plus the period. And the additional complexity is both the prescaler and the period have to be less than 65535. So these are both 16-bit values. So for instance, if the prescaler was 22 and the period is 20,802, that equation results in an output of 209 hertz. So the question is, well, if I want, I know the frequency I want to get to, I don't know the prescaler and period, how would I calculate that? And there's a little Windows program that I'll provide the link to that allows you to do that. But let's move over to that little program and I'll show you that. Okay, so here's the little tool here. It's from a group called Microelectronica. Again, as I mentioned, this is a Windows program, so I'm running this under Wine on Linux. And you basically go through, it's a little code generator. So you select your device, and they don't actually have the STM32F4 in here, but they do have F1, and they have F7 and L4 and L0, but it doesn't really matter. All I want really is the prescaler and period values. So you select the clock frequency, which is 100 megahertz, and then you put in whatever frequency you want. So let's say we put in 400 hertz and hit calculate. And you can see here it's calculated a prescaler of 3 and a period, which is in this TIM2_ARR value of 62,499. So we'll go and plug those values in, but first I need to save this. So you do project generate code, and that'll go away and basically take that specific peripheral and generate code associated with the peripheral setup. So you can see here there's the system clock there, and here's that TIM2 configuration here. And it's just taken the default values of 0 and 65535 as the prescaler and period respectively. So obviously, I'll be controlling these two values using code. I won't be just taking the default values here. So I'll create a little function that sets these couple of values here, and let's see if we can hear some output of the PWM signal. Okay, so I've created a couple of functions here called playTone and stopTone. And basically in playTone, it takes that prescaler and period value that we calculated before. So if you'll have a look here, that was prescaler of 3 and a period of 62499, which gives us that frequency of 400 hertz. So I've created a playTone value which sets those two values into the timer, and then sets that pulse period, which was the duty cycle, to half the period. So that gives me a 50% duty cycle. And then what I basically do in the code here is I play the tone, I delay for a second, and then I stop the tone, and then I delay for half a second, and then I go round and around and around. So let's program it in and see what we see. Okay, so I'll click on the debug here, and just wait for that to start up. There we go. It's broken at the first line of the code, so let me just hit go. And you can hear that 400 hertz tone being emitted from the speaker. Let me just turn that down a little bit. Okay, so let's try a different frequency. Let's try, let's say, a kilohertz. So a kilohertz. Let me just turn this down a little bit. Let's calculate that. So that gives me a prescaler of 1 and a period of 4999. So let me change this code here. Prescaler 1. And what was that period again? 4999. 4. Okay. So let's fire that off. Stop debugging. Fire it off again. And there we go. There's a 1 kilohertz tone instead of the 400 hertz tone. So anyway, that's let me just turn that down again. So that's simply how we create the tones. What I'm going to move on to next is the push buttons and the LEDs. So we'll start with lighting up the LEDs, and then we'll move on to the push buttons. Okay, so turning on the LEDs is very straightforward. So PB9 is the, let me just move that down a bit so you can see the whole screen. So PB9 is the output pin that I have configured the yellow LED on. So let's go there. To do this, you bring up the pins here. There's PB9 right there. You right click on it, you click on it, and then you just say, I want that to be a GPIO output pin. So that's basically all you need to do. That is enable that pin now. And really, because it's an output pin, there's not much I need to configure on here. I don't need to configure any of this stuff. I've just configured PB9 as an output pin. Now I can use it in the code. So let's basically compile that, generate that code again, and we'll go back and configure the PB9 as an output pin. And then to simply use it, I just want to call a simple HAL GPIO toggle pin, and then you give it the GPIOB, that's B9, so GPIO pin 9. And so I'll do that. Bear with me. I'm just going to put a little delay in there so you can see it. So let's put a 200 milliseconds delay. I've got to spell delay right, of course. 200, and let's give that a go. All right, let's run that. And just moving over to the board itself. There you can see that, there's that yellow LED flashing. And let's just increase the delay to, rather decrease the delay to 50 milliseconds. Rerun that. And you should see the delay is decreased. So just a reminder note, I'm not actually connecting the LED directly to the pin on the Black Pill. I am actually going through this transistor here, so the pin on the Black Pill is connected to the base of the transistor here through this 3.3K resistor. And then the LED, the cathode of the LED, is connected through this 220 ohm resistor to the collector of the transistor, and then the emitter of the transistor is connected to ground. And so when I get a signal here, it turns the transistor on, allowing current to pass through the collector emitter junction of the transistor. So that's the LED setup. We'll move on next to the buttons. So I'm ready to get on with the buttons now. And because I'm using a bit of C++ code for the to debounce the buttons, I want to first convert the project here to a C++ project. So you right-click on the project and then you say Convert to C++. And then also, one of the, I guess it might be a bug in STMCubeIDE, is that I also want to change this main.c to a main.cpp. Because I want to do some C++ code in there, and I don't want to have to use extern C++. So I also have selected in Project Manager here, generate peripheral initialization as a pair of .c and .h files. And what that does is it gets the timer initialization logic and the GPIO initialization logic out into separate files. And so I really want to do that because, unfortunately, if I rename this to a CPP file, the STMCubeIDE will no longer recognize it, and it won't be able to modify any of the code in here if I do that. So I've created these as separate. Now I'm going to have to be careful to not change any of the clock configuration, because once it's a C++ module, it won't actually modify that code. Okay, so the final thing I have to do is rename this, the main.c, as a main.cpp. And then this is a trick, I always forget it every single time. You have to actually clean the project before you do a build. Otherwise, it won't build properly. So clean the project, and now build the project. And I've just got a warning there, so everything's good to go. So now this is a C++ project. I can start including CPP files in there, and the first file that I'll include in there is that debounce utility that I mentioned before. Okay, so I've included these two files, bounce2.h and bounce2.cpp, in the project. I actually took these. There was some Arduino code that was originally the source of this, and I just took it in a few minor modifications and enabled it for the STM environment. I had to, obviously the STM environment doesn't have this digital read function, which is an Arduino function, and I just replaced that with the HAL function. And then similarly, it doesn't have this millis function. These both come out of the Arduino libraries, and I had to replace it with HAL-GET-TICK. HAL-GET-TICK returns the number of ticks, and each tick is a millisecond. So I've included both those files in the project. And now let's have a look at those two files, and let's see how we use them. Okay, so the first thing I want to do is set up the input pin I want to use, and that happens to be PB8 here. This is going to be for the yellow button, and I basically go down and I select GPIO input. I'm actually not, I could use interrupt-driven pins here, but I'm not. In this case, I'm just basically polling the switches. So you basically create that as a GPIO input. Let me go over here. There's a couple of parameters I need to set here. Obviously, input mode is what I need to set, but I also want to have a pull-up resistor on it. And let's just go over to the schematic and see why that is necessary. So just just swooping down here. So basically, this is the switch here. So this comes from the microcontroller. So you can see when the switch isn't pushed, it's basically open circuit. So unless I tell the microcontroller that I need to have a pull-up in here, it won't actually read it correctly when the switch isn't pushed. So that's just required on the setting there. So I just create it as a pull-up, and then let me regenerate the project here again. And this is the advantage of keeping the GPIO code out of the main.cpp. Is basically, you can see here it's actually gone ahead and regenerated another main.c. So it's not, even though I have a main.cpp there, it's not recognizing that, and it won't update the code in there. So the final thing I want to do after that is basically exclude this guy from the project. Otherwise, I'm going to get errors. So exclude that resource from the build. It doesn't, I mean, obviously it'll continue to use that on regeneration of the code. But now I'm ready to rebuild that just to make sure I have no errors. Bear with me. Let me clean that project, and then I will rebuild it. Bear with me. There we go. Just a warning there. Oh, that's interesting. Oh yeah, I've got an extra. There we go. That should fix that. There we go. Okay, so we've basically included the input pin in there. Let's move on and see how we use those bounce2.cpp to do the debouncing on the switch. Okay, so here I am back in main.cpp, and I've included bounce2.h in main.cpp. And here's the lines of code basically that set up the button. So I declare a variable of type bounce, and this is for the yellow button. So I declare one bounce variable for each button that I need. So I've got 4 buttons here. I'd ultimately declare 4 independent bounce variables. And you can see here I'm attaching, here's the port, and here's the pin ID there. So it's PB8, so that's port B, pin 8. And then I say this is the debounce interval in milliseconds. And so the whole point of debouncing is that you basically get a more reliable detection of button press. As you press a button, the controller's actually reading multiple depresses and unpresses as the spring in the switch closes. So this debounce capability gets rid of all that. And then finally, in my while loop here, I am basically testing has the button changed. So basically what this function does is it updates the button status, and it returns a true if the button has changed from the last value, whether it's gone from a 0 to a 1 or a 1 to a 0. And then on here, I'm reading the actual value of the button. So if the button is depressed, this is true. If the button isn't depressed, it's false. And all I'm doing is basically on each button press, I'm toggling the value of that LED that we set up in the previous step. So let's get this going. fire off the debugger there. It's just connecting, and then I'll continue on from there. And let me pan down onto the circuit here. So this is the button that I've set up, PB8, and you can see as I press the button, it toggles the status of the pin. So that's basically all the peripherals that we need here. We have the PWM coming out, so we've got the ability to create tones, we've got the ability to detect button presses, and the ability to turn the LEDs off and on. I mean, really, that's all the peripheral logic we need. Now, of course, this is just the start. All the complexity really here is in the rest of the code that processes the game state, and that's coming right up. So I thought the best way of describing the game code is to show the kind of internal state transition diagram and the class diagrams for the code itself. The code itself, I have put sort of comments in the code, so hopefully they're clear enough to sort of follow the individual modules in the code. But please, if you have any questions, just drop me a line in the comments. So just starting with the states, and this is the shows the state transitions of the game itself. We have the following states. So waiting, and that's where the game is waiting for a button press to start the game. We have playback, where the tones are actually being played back, the sequence of tones is being played back. And then we have response, where the user is actually inputting tones, and those tones are being checked. And then finally we have the won and the lost states, depending on whether you did the correct response or you did an incorrect response. So the arrows on the diagram indicate the various transitions between these states. So from the waiting state, there is really only one path. Any button press takes the state machine to the playback state. Once in the playback state, the game plays back an increasing number of the randomly generated tones, and on completion of that current set, it transitions to the response state. So it starts out with one tone, and then it plays two tones, and then it plays three tones. And on each of those transitions, it transitions over to the response state in order to listen for the responses. So in the response state itself, the user inputs are captured via the buttons, and they're played, both the tone and the LED is lit. And on a correct sequence, it transitions back to playback to get the next set of tones. Now, obviously, if there is an error in any one of those tones, it immediately transitions to the lost state. I forgot to mention the other transition from the playback state is once the completed set of tones are actually sent, if everything is correct here, transitions back to playback, and then instead of transitioning back to the response state, it transitions to one. So finally, the win and the lose states, all that happens there is each of those states plays a won or a lost specific tone, and then it transitions back to the waiting state. The structure of the code now, and there are three major C++ classes that are used in this. There's game state, buttons, and button. So the game state class looks after the current game modes, whether it's waiting, response, playback, and so on and so forth, and contains the implementation code for each one of those modes. In addition, the game state keeps track of the generated tones, so the randomly generated list of tones, and the playback and response index into that list of tones. Moving on, game state has a buttons instance, and buttons contains a list of all the button instances and some simple code that iterates through that list to determine which button was last pressed. And then finally, we have the button class itself, and that contains the code to interact with the hardware LED and switch, as well as the PWM timer. So to round it out, we have this bounce class here, and this bounce class here, as I mentioned before, contains code to debounce the switches. So hopefully this video has been interesting and useful. Definitely, if you have any questions on the code, I'll include links to the GitHub repo. In the GitHub repo, there's a PDF that contains the schematic in there. So if you have any questions on the schematic or the code, please drop me a line. Happy to answer any questions. Anyway, that's a wrap for now.